Hello and welcome to section 3.10, differentials. We've kind of gone back in time. We were in chapter 4, now we've jumped back to section 3.10 because differentials are needed before we go on to the unit in the next, after test 3. So we're going to go step back for a little bit from finding max and mins and the things that we've been doing recently to going back to the basic meaning of the derivative. So remember that the derivative of a function f of x is the slope of the tangent line at a point, a f of a, right? So that derivative f prime of x is just the slope of the tangent at a point. So the whole reason behind finding the derivative is to know what the function behaves like near that point, because the tangent line acts similarly to the function near that point. So we can approximate functions and analyze functions' behavior by linearizing them. In other words, looking at their tangent lines for values of x close to the point that you got the tangent line at. This is called linearizing or finding linear approximations. So if I zoom in on this point, you can see that it's hard to distinguish the curve f of x from the tangent line around x equals a, which is around between 7 and 8 in this case. So we can approximate values on the function by using the tangent line for values of x near f of a, or excuse me, near a, x equals a. I've zoomed back out in this graph, and what we're going to do is remember how you get this tangent line. So the tangent line to f at this point, remember this line has a slope of f prime of a, and so I have the slope, and I have a point on the line, which it shares with the point on the graph of f of x. So f of a is my ordered pair on the line. So this is the equation for my tangent line, f prime of a times x minus a plus f of a. So it's in slope point form. And I brought that f of a over to one side. We're going to use this tangent line to approximate function values of f. So that's what this means. So for values of x near a, f of x is approximately equal to values returned from the tangent line function, which is this side of the approximate equation. That the tangent line is also referred to as L of x. So this line is called, it's just the tangent line at of f at x equals a, but it's also called the linearization of f at a. So here's an example. The linearization is used to approximate values of, unknown values that are close to something else for a function. So in other words, let's look at the function cube root of x at x equals 8. Well, I know the cube root of 8 is 2. So to approximate the cube root of 8.05, I can expect it to be near 2, but we can get a little better approximation than that. So if we find the linearization of this function at 8, we take the derivative, that's our slope, and we evaluate it at 8, so that's the slope of our tangent line, and then we just fill in the rest of the slope point form. So the slope times x minus 8 plus f of 8. So finding the derivative and evaluating it at 8, I get 1/12. I find my other values. F of 8 is 2. So that means that when x is near 8, this line equation is similar, very close to the output from the original function cube root of x. So if I want to find the cube root of 8.05, I can use this line And when I evaluate that linear function at 8.05 and simplify, this is what I get. So this is my approximation. And notice that the graph is concave down here, so the tangent line is above the graph. So this means that my approximation from the tangent line is actually an overestimate to the real value of the cube root of 8.05. And if you find the real cube root of 8.05 from a calculator, you get this number. And again, that's rounded to many decimal places. So you can see that this is a little bit of an overestimate. So linearization, you're saying, well, why do we have this? Well, yeah, of course, we haven't always had calculators. But the one thing about linearization that's a little bit better than a calculator is that you can use it on an interval near your x value of a, right? So in this case, I know that this is an approximation to the cube root function near 8. So I can, plug in and use values near 8, and instead of just doing it one at a time in a calculator. Again, it's kind of hard to justify doing this now that we have technology, but you can see that that tangent line is a real close approximation to the cube root of x near 8.